Good morning, friends. My name is Kiran and my branch is Mechanical Engineering. Today, my subject is Engineering Thermodynamics. And here we can see that my topic is Joule Thomson coefficient evolution for real gases. And now we can observe here Introduction to Joule's Thomson effect. The Joule-Thomson effect describes the temperature changes of a real gas when it extends or compresses at constant enthalpy. Here, Joule-Thomson effect is nothing but at a change in temperature, the real gas expand or compress at constant enthalpy. Here we can observe that it is a critical phenomena in refrigeration and liquefaction process involve gases. And understanding the Joule-Thomson coefficient helps in designing efficient thermodynamic system. Now, definition of Joule-Thomson coefficient. The Joule-Thomson coefficient quantify the change in temperature with respect to pressure during the theoretical process. In mathematically, the expression you can here we can observe that 1 joule is equal to 1 kg meter square by second square. That's the unit changes of a Joule-Thomson coefficient. The sign and the magnitude of mu determine whether a gas is cool or heat upon expansion. This is the sign. There is a sign. Sign is can determine whether the gas is cool or heat. And significance of Joule-Thomson coefficient in real gases. For real gases, mu varies with the temperature, pressure, and gas composition. Mu can vary with help of the with help of temperature, pressure, and gas constant. At the same time, positive mu indicates cooling upon expansion, useful in refrigeration cycle. Positive implies that cooling upon expansion. Negative mu suggests heating, which is important for understanding gas behavior at different conditions. That was a negative mu. Now, factor influence Joule-Thomson coefficient. Molecular interaction and the equation of state significance affect mu in real gases. Temperature and pressure determine the magnitude and sign of the coefficient, and gas composition and the presence of impurities can alter the Joule-Thomson effect. Now, equation governing Joule-Thomson evolution. The Joule-Thomson coefficient can be derived from thermodynamic relation involving enthalpy and pressure. It can derive with the thermodynamic relation of enthalpy and pressure. It often utilizes the Van der Waal equation. Van der Waal equation, we know that Van der Waal equation or other real gas equation of state of accurate evolution. For accurate evolution, we need to know the Van der Waal equation or real gas equation. PV equal to nRT, and the general formula involves partial derivation of temperature and pressure at constant enthalpy. Methods for evolution mu JT for real gases. Analytically, approaches use equation of state like Van der Waal equation, Redlich wrong, or Penn borrowing Penn Binson. Penn Robinson. This was the equations we know of Van der Waal equation. And experimental methods involves measuring temperatures and changes during the theoretical process, and computational techniques including thermodynamic modeling and simulations to predict. And role of equation of a state in evolution. What are the role in this equation? Evolution of a state provide relationship between pressure, volume, and temperature for a real gas. The choice of an equation impacts the accuracy of a Joule-Thomson coefficient calculation. In this equation, we need to calculate the coefficient of a Joule-Thomson. Advanced model incorporate molecular interactions to improve the reliability of mu estimation. And practically applications of Joule-Thomson coefficient evolution is accurate mu JT evolution. It's in designing refrigeration and liquefaction system. Actually, it helps optimize operational conditions to maximize cooling efficiency. Understanding mu JT is essential in processing involving neutral gases and industrial gases separation. Now, challenges and future directions. What are the challenges and future directions? The complexity of a real gas behavior makes precise evaluation of MuJT challenging, and enhance computational models and experimental techniques are ongoing to improve accuracy. This was the accuracy of going, and future research aims to incorporate molecular simulations for better understanding of Joule-Thomson effect. Here we can observe that there is a well insulated with they are divided by a theoretical of P1 T1 and P2 T2, and L is going inside the P1 P2, and R is coming outside. Here H1 is equal to H2 is nothing but here the enthalpy is equal because of the there is totally insulated of Q and W is equal to 0. Through that we can say H1 is equal to H2. At that time we need also ideal gas equation of P is greater than Pz, and T also in some cases is equal to P2, in some cases is greater than or less than also there because of the ideal gas equation. This was the things we can observe in this table. And once we can recall what we are need what we learned in this session, here the experiment name or the title is Joule-Thomson coefficient evaluation of our real gases. Here, interaction to Joule-Thomson effect is nothing but it change in temperature, constant enthalpy. The real gas can be expand or compress. That was the main thing. And in critical phenomena of refrigeration, that was the one thing we need to involve in the gases. And a definition of Joule-Thomson coefficient is nothing but it can a temperature with respect to pressure during the theoreticalizing process. In and the unit can be we can see here 1 joule is equal to 1 kg meter square by second square. And sign conversion also we need to need a sign will be positive. We can see next slide also significance of Joule-Thomson coefficient in real gases. Here we can see that positive can imply the cooling upon expansion, that was a positive sign in refrigeration cycle. Negative can imply suggest heating at the same time of understanding gas behavior at different condition. And factor influence Joule-Thomson coefficient mainly the factors like temperature and the equation of state, like determining the magnitude and sign, that was the factors. And equation governing Joule-Thomson equation is nothing but there is a relation between the enthalpy and pressure. That was the main thing. Because of this equation, I mean this coefficient can be derived by the relation of involving thermodynamic relation like enthalpy and pressure. In this equation also we are using like van der Waals equation. Sorry, we can using equation for the getting this Joule-Thomson equation evolution is van der Waals equation. At the same time real gas equation also we are using like ideal gas PV equal to nRT. And the general formula involves a partially derivative of temperature and pressure at constant enthalpy, and this formula can be derived at the constant enthalpy of changing like the pressure and the temperature. Method of evaluating mu for real gas. How can we evaluate mu for real gas? Analytical approaches, and there is a equation like to van der Waals, one of the thing, and Redlich wrong, that was the one thing, and Penny Robinson, this was another thing. Through this scientists or this they give their equations. Through the equation only we can analyze the evolution of mu JT for real gases. And experimental methods involves measuring temperature changes during theoreticalizing process. In theoreticalizing process we can see that like methods like using the temperature changes, that's the thing. And role of equation of state in evolution, once we can observe that equation of state provide relationship between pressure, volume and temperature for real gas. In the main role in this state of evolution equation is it provide the relationship, and the relationship between pressure, volume and temperature, this can form the real gas equation. And the choice of an equation impacts the accuracy of Joule-Thomson coefficient calculation, that was the one thing. And here we can observe that 1 joule is equal to 1 kg meter square per second square, that we know. And here we can see practical applications of Joule-Thomson coefficient evolution. Accuracy evolution, it's in designing refrigeration and liquefaction, actually that is in system. At the same time it helps optimize operational conditions to maximize cooling efficiency, that was another thing. For this we can have the industrial separation of gases also, that's the one of the thing we can see. And challenges and future direction, in here we can observe there is a two there is a different like L and R. If there is condition is nothing but there is a one side is P1 and T1 and another side is P2 T2. Here we can observe there is Q and W is 0 because of well insulated. So we can say that enthalpy of both the vessel or both the side it is equal. For ideal gas PV equal to nRT, we can see P1 is greater than P2 through the H1 is equal to H2. And challenges and future directions are nothing but this complexity of real gas behavior makes precise evaluation in challenging. That was the one thing. And last thing we need to know or we need to see that future research aims to incorporate molecules simulations for better understanding for understanding of Joule-Thomson effect. That was another thing for the challenges which we see in future direction. And at the last we can see thank you.